In this video, I'm going to give you some tips for solving the ALEKS problem called predicting the relative stability of ionic crystals from a sketch. So this problem is going to give us 4 different pictures of 4 different ionic substances, and our job is to rank them in order of their energy lowest to highest. Of course, there are going to be a lot of different variations of the crystals that you're dealing with in your particular problem. So what I'm going to do is show you how to solve this exact version of the problem, and then I'm going to also talk about how you would go about solving different versions of the problems, because you're not going to see these exact same 4 pictures over and over again. So when I'm looking at this particular problem, the first thing that I'm looking for is the pattern of positive and negative charges within the crystal structure. And you can see that in this particular crystal, I have alternating negative, positive, etc. This structure, again, I have alternating positive, negative charges as I go across the row. This one, I have adjacent positive charges, adjacent negative charges, and then here I'm back to an alternating pattern again. The alternating pattern, alternating positive, negative is a good situation. So alternating positive and negative charges is good, and adjacent positive, negative, that is bad. Since I have only one of these types of structures where my charges are adjacent to each other, that is going to be my number 4 least stable, least stable crystal. The rest of these are going to be higher. Now, you may have a situation where you have 2 that kind of resemble this pattern. Don't worry, I am going to talk about how you would distinguish them from each other. Of my remaining, I have alternating, which is a good situation, alternating positive, negative charges. So to tell these apart, the next thing that I'm going to look at is this structure here, which has 2 plus charges. The other structures are plus 1s and minus 1s. This one is plus 2 charges. So if we're dealing with a situation where I'm trying to distinguish which of these is better, they're all alternating. The one that has the higher magnitude of charge is definitely going to be the one that is the most stable. So this is going to be my most stable, and then we can kind of make a note of that. Plus 2 minus 2 is better than plus 1 minus 1. Plus 1 minus 1 isn't bad. I don't want to draw a frowny face. I'll just draw a whatever face. So if we have plus 2 minus 2, that is going to be a more stable situation than plus 1 minus 1. Of course, the alternating versus adjacent charges, that is going to be the number 1 thing you should look for. That's the biggest deal. This is just always super bad. It doesn't matter what the charges are. If you're trying to break a tie, meaning if you have multiple alternating patterns and you're trying to break a tie, look for the charges, the magnitude of charges. Or if you have multiple adjacent, so if I had 2 versions like this, where I had adjacent positive charges and adjacent negative charges, I would be looking at the magnitude of the charges to help me figure out which one is better, which one is worse. So for these ones now, I'm down to these 2. These 2 are pretty similar in that they are alternating. That's good. And also they're similar. They have the exact same magnitude of charge. So how am I going to tell these guys apart? The third variable that we're going to look at is the size. The smaller these atoms are, smaller is better, and larger is not necessarily bad. So again, I'm not going to make a frowny face. I'm just going to make a whatever face. The smaller the ions are, the better the situation is, the more stable it is. So this one, which definitely has smaller spheres, this one has larger spheres. This is going to be my number 2, second most stable. This one is going to be my number 3. Now, whatever your particular pictures look like, you should definitely apply these different things in this particular order. So first of all, sort them out based on if they have alternating or adjacent charges, and then after you've sorted them out that way, move on to the magnitude of the charges, plus 1 minus 1, plus 2 or minus 2, and then once you've sorted those ones out, take a look at the sizes of the actual ions. I do want to let you know that some versions, you might be looking at this right now, some versions of the problems don't have the ions completely packed together, so they have kind of a staggered arrangement looking like that. I'm trying to make all these the same size. I'm not doing a great job. This one can be a little bit trickier to figure out when you're dealing with alternating versus adjacent. So this one is kind of weird with the alternating adjacent. With this particular one, you are going to see adjacent charges in columns. So you're going to see positive, 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 negative, 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 negative. This is the bad adjacent situation. These ones, I meant these ones to be negatives. So this one where your adjacent charges are coming down in columns, that is the bad situation. For this particular one, the good situation is alternating positive, negative, positive, negative, positive. And then the pattern alternates itself down here. So this particular pattern can be a little bit tricky because if you have like negative, 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 positive, 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 negative, negative, it is a little bit tricky because technically you are looking at rows of negative charges and rows of positive charges, but because of the gaps here, they're not literally adjacent charges. Like these negative charges are not literally adjacent to each other. They are staggered with these positive charges. So this particular pattern, this is not what we would consider adjacent charges. We would consider this alternating charges. The atoms that they're in contact with, they are in alternating charges. So this is good right here. And the bad version, I'm only going to draw a little bit of it. The bad adjacent version of this would have your charges like that. It's so small and so messy. I apologize. Like that. So this would be the bad version. I've also seen, when we're talking about the sizes, I did see a variation of this problem where the ions were different sizes within the structure. So it had like really large anions and then really small cations. So it kind of looked like this. That was kind of crazy. But for that particular problem, you're just going to take a look at the fact that you have large ions and you're going to lump this whole entire thing in with the large ion category. You're going to ignore the small ions. So when you're using this variable, you're going to look at the biggest ion that you have in the mix. You're going to ignore a smaller one if you have two different sizes. And you're going to rank it like that. So if I had this and I was comparing it to this, which is quite a bit smaller, or at least that was my plan to make it smaller, I would say that this was the larger version and this was the smaller version. And I'm comparing the largest ion here to the largest ion here. Good luck with this problem. It is kind of funky, but I think if you're patient with yourself, you'll have no problem.